Hi, I'm Sneha. I'll be talking about a paper called MatFormer on adaptive training. This is work I did with a bunch of folks at both DeepMind and at University of Washington. So transformers get super expensive as you scale up, and different parts of your transformer are more expensive than the other. And one approach to look at this is thinking about adaptive architectures, which is thinking about coming up with training algorithms and architectures that dynamically adjust your computational cost per token based on your input data, your task demand and budget, or how many resources you have available right now. You can adapt your computational cost in a whole bunch of ways. So this is a bunch of work. Some of this was presented or will be presented at this workshop today, or are pretty recent papers. You could change the depth of your model depending on your input. You could even change your model altogether depending on your input, which has been pretty popular. There are even more approaches than the specific one I highlighted. Or if you're considering MOE architectures, you could even change the number of experts depending on your budget, or even change the expert size. So we specifically build upon some ideas that were first proposed in computer vision. This is Matryoshka representation learning. So what we decide to do here is say, okay, we think that we can learn the same representation of images in activation space at different granularities within the same activation space. So specifically what we mean by that is, suppose we have this matrix, this yellow matrix over here that is your output activations. We will train our model such that, the first 1/16 of this is going to be a super coarse representation. And then the orange one that's a little bigger is a little bit more detailed, and so on. And for vision tasks, you find that doing this actually you actually end up with representations that are about as good as training from scratch, and sometimes even work way better than doing post-hoc compression methods. So what we specifically do is decide to, instead of learning this granularity in the activation space, we learn this in the weight space. And by that, what we do is compute the loss for every single granularity. And throughout this talk, when I say granularity, I mean the model size that we want to consider. We compute the loss for each granularity that we want to train our model to be good at dealing with, and optimize this loss jointly. And throughout the talk, I'll use sizes in English, XL, L, M, and S, to denote different matrix sizes. And for the experiments that I discussed in the paper, I will mostly be changing the size of the MLP hidden representation, but this method is pretty general, and you can extend this to the attention heads, the input representations, or even embeddings of a transformer model. And another interesting property that we will show of the models that we train using this method is that even though at train time, we train for 3 or 4 different model sizes, you could actually just say, actually I want to train the first half of my model on the full size of the transformer XL, and then change the model size to the smallest model size that we've learned, and then get model sizes that are in between. And we find that we can actually end up with models with in-between sizes that we never really trained for, but they're just as good as training from scratch. So I'll talk a little bit about our experimental setup. So we train models. So these are the model scales for the full model, the XL model. We train models up to about 2.6 billion parameters. And we explicitly train for 4 different model sizes. And the smallest submodel size that we train within the main model is 1/8 of the hidden dimension. And we also have baselines denoted by baseline XL, L, M, and S, which are the exact same shape as the different submodels that we're optimizing for. So overall, like we find that there's little to no loss in our dev test log perplexity and our downstream evals. And without explicitly training for these models, we are also able to get in between model sizes. And we also are able to use these models to use rooting techniques. In these experiments, we show experiments for speculative decoding, which I will also cover a little bit for those who might not be familiar later in the presentation. And we find that these work way better than just using independently trained baselines. So over here we show the perplexity results for the 2.6B parameter model, which we trained for about like 160 billion tokens, which is like slightly overtrained, but not by that much. And for our evaluations, like the log perplexities are within about 0.04 of the baseline for the same number of tokens. And the downstream evals are within about 0.5%. And also like over here, the stars are the in-between size models that I was talking about, which we denote as mix and match throughout this presentation. And these are downstream evaluations where also like our technique performs very similarly to independently trained baselines. And we also find that our technique scales about as well as vanilla transformer language models. Over here, like what we do is we train a bunch of models of different sizes, and we also are plotting the losses of all of the submodels in addition to the main models. And we find that like all the XL, large and medium and small models follow the same scaling law. So earlier I was giving an example from Vision about how like if you train models in this way, you can end up with a coarse to superfine and detailed and more expensive representation of the same input. And we find that property carries over into text generative transformer models. So we do experiments where we measure this property called consistency. So consistency is the accuracy of the smaller submodels that we train when we assume that the output of the main model is the ground truth. So what we're trying to measure is like, how often do the smaller models we train agree with our larger models? And we compare that to, like how much do independently trained models of similar sizes, like say the base XL baseline and the small baseline, how often do they agree with each other? And as for why we would care about consistency specifically for foundation models, like techniques like speculative decoding actually become more performant when you have a more consistent model. And over here, like in this, and I will go into the specifics of why that is so for the techniques like speculative decoding in the next slide. But over here, what we're seeing is that MatFormer models, when compared to the output, the consistency of MatFormer models are way higher than when you compare the consistency of two similarly shaped baselines. So so a little bit about speculative decoding. So speculative decoding is an algorithm that you can use if you have a really large model and a really small model to speed up your, to improve the latency of decoding. So what you do over here is do a lot of decoding with your small model, but use your large model as a verifier in order to get latency savings. And over here, you fall back to the large model when your small model messes up. So you could see how, like, oh, if your small model is actually agreeing with the larger model way more often, you'll end up with better, a much faster setup. So empirically, we find that this is actually the case. The consistency gains that we measure in a few slides before, we find that that holds up with our speculative decoding experiments. So what we do over here is we take a 2.6 billion verifier model and a 1.5 B draft model. In practice, like, you can even use a way smaller draft model than this and get even bigger speedups. But this is the setup we went with. So what we measure here is we see, like, oh, compared to just using the 2.6B model, like, how much faster do we get when we use a speculative decoding baseline algorithm. And we find that we get about 10 to 15% gains depending on what we do. Slightly more, if just using the baselines gives you a 10% gain, you get about a 15 to 16% gain using MatFormer models as the backbone for this algorithm. And we also do some vision experiments, specifically on classification and retrieval. Okay, I'm doing okay on time. So first, we do this on a VIT setup with ImageNet 22K and 1K data sets. So first we look at classification and measure the top one accuracy of these models on ImageNet 1K. And we find that these work about as well as independently trained baselines. And then we also look at hierarchical encoding for encoders for retrieval. By that, what I mean is when you're doing image retrieval, you could use the largest model for building your index, but use like a smaller query encoder to get way faster retrieval results. So what we find over here is, like, without actually explicitly trying to train the setup to work hierarchically, we get way better results when we use MatFormer VIT models for retrieval compared to our baselines that are independently trained. And for future work, a lot of which has been done by different folks in the community and our collaborators, you could extend jointly optimizing submodels within the same representation space to other parts of the model for way more inference savings. And we also mostly just use speculative decoding to decide how to choose which submodel we are using for a given input, which some folks have done work on. And you could even go further when it comes to reordering your representations for quantization, like over here, and end up and be able to like use even like get your 2-bit representations and 4-bit representations that are better than independently trained quantized models at that level of detail. And this also works for different architectures. Some folks have tried this for Mamba. There are also non-trivial, interesting things you could do both on the algorithm and hardware side to make this work for MOEs.
So, if I understand correctly, in the MatFormer, you do interleave forward for the small model, forward for the medium model, and the large model. But you have to. It's quite hard to interleave properly on a hardware. If I have like a certain amount of GPU, it's mean when I do a forward for the small model, I'm probably underutilizing the GPU. While if I do forward with the big model, I'm using fully those capacity.
Yeah.
Could you maybe train in parallel on different kind of node of different size, each of the subset at the same time?
I think that's totally possible. We did train larger models and found that maybe like a 10% overhead if you just like do this out of the box with like reasonably good sharding. But yeah, I think doing something like parallelly training things on different devices could make sense.